Level 1. Time. Time is unquestionably one of the most essential aspects of physics. It serves as the measure of change, the invisible framework that enables us to track the universe, compare events, and define the sequence of cause and effect. Unlike physical objects, time lacks shape, weight, or form. It exists as a continuous flow, moving forward without interruption. At its core, time provides structure to the universe. A second is determined by the vibrations of atoms, a day by the Earth's rotation, and a year by its orbit around the Sun. These natural cycles lend time a tangible presence, enabling us to measure and organize reality. Without time, events would lack order, and motion would be meaningless. However, time is not just a means of measurement. It is a fundamental dimension of existence. It dictates how processes unfold, from the movement of celestial bodies to the rhythms of biological life. Plants grow, tides shift, and seasons change, all governed by the passage of time. Position. This is the fundamental. Level 2. Position and position is the reference point of motion. Every object exists somewhere in space, and describing its position is the first step in understanding movement. However, position is not absolute. It is always measured relative to something else. In physics, position is defined using a coordinate system. A simple number line can describe motion in one dimension, where moving forward increases position values and moving backward decreases them. In 2 dimensions, coordinates on a map pinpoint exact locations. In 3 dimensions, objects move through space with X, Y, and Z, coordinates defining their position at any given moment. But position is not just about location. It depends on the observer. A train moving past a station appears in different positions depending on whether you're inside the train or standing on the platform. This idea, known as the frame of reference, is crucial in physics. The same object can have different positions depending on the point of view, which influences how we measure motion. Position also plays a key role in navigation and measurement. Whether tracking a satellite in orbit, locating an earthquake's epicenter, or mapping the movement of tectonic plates, understanding position allows us to describe and predict how objects move through space. Level 3. Distance. Distance is one of the most essential concepts in physics, describing how far an object has traveled from one point to another. Unlike position, which specifies a location, distance is purely a measure of length. It accounts for the total path covered, regardless of direction. Imagine a car moving along a winding road. If it starts at one point, follows a curved route, and arrives somewhere else, the distance traveled is the sum of all the segments of its journey. Even if the car returns to its starting point, the total distance remains the entire length of the trip. Distance is a scalar quantity, meaning it has only magnitude, not direction. This distinguishes it from displacement, which measures the shortest straight-line path between 2 points. For example, a person walking around a city block may travel a long distance, but their displacement is simply the direct separation between their starting and ending points. In everyday life, distance is measured using units like meters, kilometers, or miles. It helps us navigate roads, measure heights, and calculate depths. In science, precise distance measurements are essential for mapping microscopic structures, analyzing planetary motion, and even understanding the scale of the universe. From the smallest atomic interactions to the vast distances between galaxies, the concept of distance allows us to quantify movement and size. Whether measuring the span of a room or the reach of a star, distance serves as a foundation for understanding physical space and motion. Mass, one of the most fundamental levels of physics, defines the presence. Level 4. Mass is the measure of matter, giving everything from the tiniest particles to the largest galaxies a measurable existence. Without mass, objects wouldn't have substance, weight, or resistance to motion, fundamental traits that shape the physical world. At its core, mass quantifies how much matter an object contains. It remains constant, regardless of location or external forces. A bowling ball is harder to lift than a tennis ball because it contains more mass. Unlike weight, which depends on gravity, mass is an inherent property of an object that does not change whether it's on Earth, the Moon, or floating in deep space. Mass also determines how objects interact through gravitational attraction. The reason planets stay in orbit, why things fall when dropped, and why stars cluster together is due to mass. More massive objects exert stronger gravitational forces, influencing everything from planetary motion to the structure of the universe. In everyday life, mass is measured using balances or scales, which compare an object's resistance to gravitational pull. In space, where gravity is absent, mass is determined by how much force is needed to accelerate an object. These measurements are crucial in physics, engineering, and even daily activities like cooking or construction. Mass is not just a number, it is the foundation of all physical interactions. It dictates how objects respond to forces, how they interact with gravity, and how the universe itself is structured. Understanding mass is the first step in unraveling the fundamental principles that govern the physical world. Motion is the foundation of change in the universe. From the drifting of galaxies to the shifting of a grain of sand, nothing remains truly still. Even Level 5. Motion. In the most motionless state, atoms vibrate, planets rotate, and space itself expands. Motion is not just movement, it is the defining characteristic of existence. At its simplest, motion is the change in position of an object over time, relative to a chosen reference point. A car passing a stationary observer on the sidewalk is in motion, yet to a passenger inside, it appears still. The movement of an object can only be described when compared to something else. Motion is always relative. Every type of motion follows specific patterns. Some motion is uniform, where an object moves at a constant rate in a straight path. Other motion is non-uniform, where speed or direction changes over time. The swing of a pendulum, the orbit of the moon, or the rise and fall of ocean tides, all are forms of motion shaped by forces acting upon them. Motion can be linear, like a falling rock, or circular, like a spinning wheel. It can be periodic, like the back and forth swing of a clock's pendulum, or chaotic, like the erratic movement of molecules in a gas. No matter the form, motion governs how objects interact, how energy transfers, and how systems evolve over time. Understanding motion is essential to understanding the physical world. It dictates the patterns of nature, from the simplest falling leaf to the vast movements of celestial bodies. Recognizing and analyzing motion is the first step in exploring the deeper principles that define the mechanics of the universe. Level 6 measures how quickly something moves from one place to the rate at which distance is covered over time, making it one of the most fundamental aspects of motion. Whether it's a car traveling down a road, a person running, or sound moving through the air, speed describes how fast an object is in motion. At its core, speed is simply the total distance traveled divided by the time taken. If a train covers 200 kilometers in 4 hours, its average speed is 50 kilometers per hour. Since speed only tells us how fast something moves, not in which direction, it is classified as a scalar quantity. Speed is everywhere in daily life. Walking casually, a person moves at about 5 kilometers per hour. A plane cruises through the sky at nearly 900 kilometers per hour. The fastest land animal, the cheetah, can reach speeds of over 100 kilometers per hour. But even these speeds are slow compared to astronomical speeds. The Earth orbits the Sun at about 107,000 kilometers per hour, and light itself travels at nearly 300,000 kilometers per second. Understanding speed allows us to measure, compare, and predict movement in everything from transportation to natural phenomena. It helps engineers design faster vehicles, scientists study motion in physics, and astronomers calculate distances across space. Whether it's measuring the pace of daily activities or tracking objects moving at cosmic scales, speed is an essential concept that defines how things move through the world. Level 7. Velocity. Velocity is not just speed, it's speed with direction. While speed measures how fast something moves, velocity specifies both how fast and in which direction. This distinction makes velocity a vector quantity, meaning it has both magnitude and direction. Imagine a car moving at 60 kilometers per hour. If it's traveling east, its velocity is 60 kilometers per hour east. If it turns west at the same speed, the velocity changes, not because the speed changed, but because the direction did. This makes velocity a more complete description of motion than speed alone. In everyday life, velocity helps describe motion more accurately. A plane flying at 800 kilometers per hour is not just moving, it has a velocity based on its direction. The wind's velocity determines whether a flight is delayed or arrives early. Ocean currents influence ships based on their velocity. Even in sports, understanding velocity is key, whether it's tracking the path of a baseball or calculating the trajectory of a soccer ball. In physics, velocity is essential for describing motion across all scales. It defines how objects move, how trajectories are calculated, and how motion is predicted. Whether it's tracking planetary orbits, measuring fluid flow, or studying moving particles, velocity allows precise analysis of movement. By knowing both speed and direction, velocity provides a complete picture of how objects travel through space. It forms the foundation for understanding motion in mechanics, navigation, and even astrophysics, making it one of the most fundamental concepts in physics. Level 8. Acceleration. Acceleration describes changes in motion. Whether a car speeds up, slows down, or turns a corner, it is experiencing acceleration. Unlike speed, which measures how fast something moves, or velocity, which adds direction, acceleration measures how quickly velocity changes. At its core, acceleration is the rate of change of velocity over time. For example, if a car is moving at 20 meters per second and increases to 30 meters per second in 5 seconds, it has an acceleration of 2 meters per second squared. But acceleration isn't just about speeding up. It also includes slowing down, known as deceleration, and changing direction. A car turning at a constant speed is still accelerating because its velocity is changing. Acceleration is a key concept in describing how objects move, from everyday activities to astronomical phenomena. When you push off on a bicycle, the increase in speed is acceleration. The jolt you feel in an elevator when it starts or stops is acceleration. Even Earth itself accelerates as it follows its curved orbit around the Sun. Gravity is one of the most familiar sources of acceleration. Any object falling freely near Earth's surface accelerates at 9.8 meters per second squared, regardless of its mass. This explains why two objects dropped from the same height fall at the same rate, assuming air resistance is negligible. Whether tracking a moving vehicle, studying falling objects, or analyzing planetary motion, acceleration provides a fundamental way to describe and predict changes in movement. Understanding acceleration allows us to analyze motion with precision, making it an essential concept in physics. Force. Nothing moves, stops, or changes without force. It's the invisible. Level 9. Force is behind every motion, from a falling raindrop to the movement of massive tectonic plates. Without force, the world would be static. No flowing rivers, no shifting clouds, no movement of objects. At its core, force is simply an interaction that causes a change in motion. It can make something start moving, stop, or change direction. A force applied to an object can speed it up or slow it down. The more force exerted, the greater the effect. Pushing an empty cart is easy, but a loaded one requires more effort. This is because greater mass requires a greater force to achieve the same motion. Forces come in many forms. Contact forces require physical interaction, like friction and applied force. Try sliding a book across a table. Friction resists the motion, slowing it down. Push a door, and it moves in response to the applied force. Forces can also be balanced or unbalanced. When equal forces act in opposite directions, there is no movement, like two people pushing against each other with equal strength. But when forces are unbalanced, motion occurs. The stronger force overcomes the weaker, setting objects into motion or altering their speed. From the pull of a stretched rubber band to the impact of a hammer striking a nail, every action is governed by force. Whether subtle or immense, force is the reason objects move, interact, and respond to their surroundings, making it one of the most fundamental principles in physics. Inertia. This plays a crucial. Level 10. Inertia. Inertia plays a crucial role in shaping everything, from daily experiences to large-scale cosmic interactions. It's the reason why a bicycle stays upright when moving, but topples when stationary, why astronauts in space continue floating without resistance, and why heavier objects require more effort to move or stop. Inertia isn't just a property of objects, it's a fundamental characteristic of matter itself. Engineers and scientists rely on inertia to design safer vehicles, stable bridges, and efficient machinery. Crumple zones in cars are built to counteract inertia during a crash, absorbing impact forces to reduce harm. In sports, understanding inertia helps athletes control motion. Whether it's a runner maintaining momentum or a gymnast sticking a landing, inertia plays a key role in their performance. Even in space exploration, spacecraft must account for inertia, using precise thrusts to adjust their course. Since objects in a vacuum will continue moving indefinitely without external resistance, inertia becomes a critical factor in space navigation. On a grander scale, inertia governs planetary motion. The Earth orbits the Sun, not because it is actively propelled, but because inertia keeps it moving, while gravity bends its path into an orbit. The same principle applies to galaxies, where vast celestial bodies move in predictable patterns due to their own inertia. Recognizing inertia allows us to predict movement, control forces effectively, and innovate in fields ranging from transportation to astrophysics. Whether it's the stability of buildings, the efficiency of machines, or the mechanics of motion, inertia is a silent but ever-present force shaping the physical world. Momentum. It is the reason a moving train takes miles to stop, why a bullet